Hello and welcome to our final topic in concepts of probability. In this discussion, we will be talking about decision errors. In other words, it is possible to be wrong. And so this particular section is just ripe for writing test questions. So I want to warn you, you will very likely have a test question on, like, say, a CPH exam, about decision errors and statistical power. So let's spend a little bit of time on this topic because I think it's really important to kind of thoroughly understand what it is that we're deciding when we make these decisions, reject and fail to reject the null, and how that can kind of go wrong. So let's start off by making a little table, and you will see this over and over again. So this table is your friend, and just draw it here. And this table, this 2x2 table, represents both the decision and the truth. And so by what I mean by decision and truth is the decision can either be fail to reject the null or reject the null. And the truth can be that the null is true. In other words, yes, the average is equal to 170 in the population, or the truth can be that the null hypothesis is false. Now notice again, we're always referring to whether the null hypothesis is true or false. We don't talk about whether the alternate is true or false. It's implied by testing the null hypothesis, but the null hypothesis is the one that we're testing. So first of all, I want to give you an example of when we did not make an error. So in other words, we were correct. When we made that decision, reject or fail to reject the null, we made the right one. And those two situations are right here and right here. In other words, if we reject the null hypothesis and the null hypothesis was false, it's like perfect. That's exactly what we should have done. We rejected a false null hypothesis. It was false and we rejected it. So we were correct. On the other hand, if we fail to reject the null hypothesis and turns out if we had perfect knowledge of everything and that null hypothesis is true, we were correct again. We shouldn't go around rejecting null hypotheses that are true because they are true. And so we should say, okay, you are true. Now, there are two situations left here that we made the wrong call. And that is, and let me put this in red, the wrong call is if we reject the null hypothesis, but that null hypothesis was true. We should not have rejected it. This is called a type 1 error. And this is the type of error that we make when we're rejecting the null hypothesis and it's out in that tail where the null hypothesis was actually true. Let's see if I can get back to it pretty easily. Like let's say it's that the null hypothesis just happens to be out here, happens to be the 2.5% that falls outside of that range. But, so it just happened by chance, but we made an error because that null hypothesis was actually true. The other situation happens when we fail to reject the null hypothesis, but it was false. It should have been rejected. And so this is called a type 2 error. And so we make a type 2 error when the null is false, but we somehow weren't able to reject that. So let me map these down here at the bottom. I'm going to first map the correct ones. So correct means you made the right choice. And so let's walk through this. If you're trying to create a sentence out of this, you would say, I correctly failed to reject a true null hypothesis. So that's here. The decision was to fail to reject, and that's this one. And the truth is that the null hypothesis is true. So if I correctly fail to reject a true null hypothesis, I was correct. I made the right choice. I didn't make an error. The other way of being correct is right here. I correctly, let me change to green. Sorry, no, still blue. I correctly rejected a false null hypothesis. So again, if I reject it and it was false, I did the right thing. So here's my null hypothesis. Now, there are also two ways of making the wrong choice. In other words, an error is being incorrect. And so here I'm going to, in this quadrant, I make an error. In other words, I am wrong. And I don't want to be wrong. It's possible to be wrong, but I don't want to be wrong very often. So if I reject the null hypothesis and it was true, then that is an error. That means that I was wrong, I was incorrect. And the other way of making a mistake is to fail to reject a null, and that null hypothesis was false. So this is basically right here taking the table above and turning it into sentence form, because a lot of things on exams are just written as a sentence. Now you can take that and you can convert it back to this table that we created up here, just for your own help while you're taking the exam, but just recognizing that if it says you did something incorrect, then you're stuck with either a type 1 or a type 2 error, basically. You rejected the null hypothesis, but it was true, or you failed to reject it, but it was false. So those are the different ways that you can make a mistake. So let me fill a little bit more information in here for this particular table. And this has to do with kind of going back to the confidence that we've been talking about all along. This quadrant right up here on the left-hand side is where we would look at our confidence. You've heard us talk about kind of like this statistical significance or the confidence. This is our 95%, kind of that middle area where we're pretty sure we made that right choice. And the z-value that goes along with that is 1.96. Remember over here when we were creating this table, we used the number 2, but this really is 1.96. It's just so close to 2 that it's easy to kind of round it, 1.96. So technically, the true z-value for that position is 1.96, just so you know, if you see that number in the future. Over here on the right-hand side, this is a new concept for you. This is called power. And we often will say our ability to correctly reject a null hypothesis that is false. So this is the ability to correctly reject a null hypothesis that is false. And we want to reject a null hypothesis that is false, and it's the power that allows us to do that. Now, again, by convention, a lot of people have said, you know, 80% is a pretty good level for that. Sometimes we want to go to 90%. Theoretically, we could do even more than that, but it's a trade-off because sample size and power and confidence are in flux. It's kind of like a seesaw or a teeter-totter. If power goes up, then confidence ends up going down. And a lot of times people will say, oh, we definitely don't want to make a type 1 error. That's really bad. We don't want to reject a null hypothesis that's true, because then we're sending information out there into the world that's incorrect. And so here we have our confidence and our power, and if one goes up, the other one goes down. If a different one goes up, then the other one goes down. So they're kind of like they're a seesaw. The z-value that goes along with a power of 80% is 0.84. Now these numbers are going to come in handy when we get over here and start talking about power specifically. So I've filled that in for you right here. Now, the other ones that we have talked about are type 1 error, and this is our alpha level. Remember, we've talked about alpha. And this typically is, whatever is the opposite of 95. So this is 0.05. And this is our p-value, and it's the probability of a type 1 error. In other words, did we reject the null, but the null was actually true? And so if we go back to our table over here, remember how here we have our p-values? Oops, we have a pen. We have a 2.7% chance of rejecting the null hypothesis at when we had this scenario where we were looking at 1.5. But the null hypothesis was actually true. And so that's what we're looking at here. We have the possibility of making that mistake. It's possible to be wrong. We could have been wrong. We rejected the null based on this p-value, based on the cutoff, based on a 95% confidence interval. But it is possible 2.5% of the time in that particular scenario, 2.7%, we could have been wrong. Similarly, and this is a new concept for you, this type 2 error is called beta. What that means then is power is 1 minus beta, in case you were wondering. And beta is the probability of a type 2 error. And what that means is that we failed to reject the null, but the null was false. Now the thing that is interesting here, and I want you to hold this in your head, when you go and you read research papers, we only knew about our sample. We only know about our particular decision. We know if we failed to reject the null or we rejected the null. And if we failed to reject the null, our only two choices is we were right or we committed a type 2 error. If we fail to reject the null, we can't commit a type 1 error because we're not even in that row. So failing to reject the null means that we could have failed to reject the null and we were right, that the null hypothesis was true, or we could have failed to reject the null and made a mistake because the null was actually false. Now, in our scenario up here, over on the right here, we failed to reject the null. Remember, we were testing whether this sample mean of 173 is different from 170. Now, yes, 173 is different than 170, but is it statistically significantly different? No. The thing about power is that we could have just not had a big enough sample size in order to detect that difference as being statistically significant. Remember, it all keeps going back to the sample size. So this beta is the probability of a type 2 error, and if we take the opposite of this 80%, that means that 0.20 or 20% of the time, if we have our power set at 80%, that 20% of the time we're actually going to be wrong. The other decision that we can make is that we reject the null, and then if we reject the null, there are two possible choices. Either we were right and the null hypothesis truly was false, or we made a type 1 error. In other words, we rejected the null, but it was actually true. And so that's what we saw in this other scenario where here we rejected the null, but we had that 2.7% chance of making a mistake. We could have been wrong. It's possible to be wrong. So that's what those four quadrants all kind of stand for. The last thing that I need to tell you about these decision errors is that if we keep testing and doing what's called multiple testing right here, if we do multiple independent or one sample t-tests over and over and over again, we get 0.05, error with one, 0.05, error with another, 0.05, and over time you don't technically actually add them together. But what happens if you're doing multiple testing is that your type 1 error goes up. And so intuitively, that makes sense. It's not exactly proportionate to the amount of possible error that you have for each one of those tests. The math behind it is a tiny bit different than that. But if we go back to this example right here that we've been using all along, let me see if I can find another color to write on the graph. Let's say that I do a whole bunch of tests. You know, a lot of them are kind of fall within the range, but every once in a while we're going to end up with, just by random chance, we're going to end up with a mean that's farther away. And so if I do enough of them, then the chances of getting one of those actually goes up and continues to go up with the more tests and more tests that we do. So with multiple testing, type 1 error goes up, or the chances of rejecting the null hypothesis when the null hypothesis was actually true. So that's kind of an important concept that you'll probably see as we continue on through our discussions, and that's the kind of thing that the test writers love to write. So if it's possible to be wrong, then what do we want to do about it? The answer to all our questions in statistics is sample size. So sample size decreases the chances of being wrong. And the way it does that is by making the results that we get more and more and more easy to interpret. So I'm going to write an equation here, and so I hope this doesn't scare anybody too much. I'm going to say that the sample size we need, and this is kind of an important piece, because remember, all along we've been talking about we have a population, we take a sample from it, and this is a really important question that people ask biostatisticians all along. How big of a sample do I need? So I'm going to show you how to think about this intuitively. So if I have my sample size here, the sample size is, and this is kind of a generic equation for sample size. It's actually different for each kind of statistical test, but in general, these are the parts that are included. The sample size is related to the standard deviation, or how far the sample is spread out. You know, it could be kind of wide, or it could be that the sample is narrower distributed. So this sample size, or standard deviation squared, times, and I'm going to say the z that goes along with our confidence. So z of confidence plus z of power squared, and all of that divided by what we're going to call a meaningful difference. And we're going to square that too. So our sample size is directly proportionate to the standard deviation. It's directly proportionate to how sure you are of your results, these z values, and it's inversely proportional to the difference that we're looking for. And by difference, what we mean is how far away our sample mean is from that population mean. So this goes right in there. Now, hopefully you've seen all of these parts before. You know what standard deviation is. You know about these z values. You know about x bar. You know about mu. So and also what you can remember is that unless you choose something different than 95% confidence and 80% power, the value that we would put in here, remember the z that goes along with the 95% confidence is 1.96. The z that goes along with the power of 80% is equal to 0.84. So this really just keeps staying the same, these z values. The standard deviation, I really, really, really want you to intuitively understand this. So let's say, let me actually erase this. This seems kind of... If we have a sample, and that would be blue, if we have a sample that is really wide in distribution, and here's the sample mean. And we say, you know, we want to test if that is different from maybe this value right here, mu. Here's our, oops, put X bar down here. We want to test if this difference is important. If that is spread out as far as this is, then maybe this population mean is kind of reasonable. Maybe that's okay. On the other hand, if my standard deviation is narrower, and I have this same kind of population, and I have an X bar here, and I'm testing it against a population mean that's this far out, you would just look at that intuitively and say, wow, that's a long ways off. That seems really far away. You know, maybe that would by itself make it statistically significant. So the thing you should remember is if the standard deviation goes up, in other words, it's wider here, that means that you need a larger sample size in order to be able to find out if that is statistically significant or not. Similarly, if instead of a mu here, if this difference that I'm trying to detect is actually smaller, if instead I have a mu that I'm trying to test and it's right here and I'm trying to test a smaller difference, I'm going to need a much bigger sample if this difference I'm trying to detect goes up, then, or sorry, the example I just gave you was that it went down. If this difference that I'm trying to detect gets smaller, that's another reason that I'm going to need a larger sample size. And so if you think about that kind of intuitively, let's say we want to test and see if we can get a 1 millimeter of mercury of blood pressure. You know, we can go from 120 down to 119. We're going to intuitively need a really big sample in order to detect that really small change. And so here's our amount of difference that we're trying to detect. If we're trying to detect a really small change, we're going to need a big sample size. And if that underlying population is really spread out, right here, my standard deviation is large, then I'm also going to need a much larger sample size in order to be able to detect that. So those are a couple of the reasons that I would need a larger sample size. Inversely, the same thing would be true. If my standard deviation gets narrower, then my sample size that I need to pick up on that, it actually goes down. If I'm okay trying to pick up on a big difference, if I can talk about weight loss not in terms of 1 pound or 2 pounds, but if I say my intervention is going to cause weight loss of 50 pounds, then I'm not going to need nearly as big of a sample size in order to detect that meaningful difference. We're calling that our meaningful difference. Now, a lot of people will ask me, what do you mean by meaningful difference? And this all goes back to something that has to do with clinical importance. And so if you think about there's a clinician, they're working with patients, or there's a health worker, they're working with a population, we want to find something that's actually meaningful. And so that clinical importance sometimes is a more relevant concept than statistical significance, because that kind of has a little bit of artificialness to it. In summary, I want to talk about what this sample size then means in terms of power. So if my sample size goes up, what that means is that I am more able to correctly identify a false null hypothesis. In other words, I have the power to reject a false null hypothesis. And so here I am in my reject a false null hypothesis, and I was right. Power, sample size, a lot of times you'll hear people say sample size and power, kind of like they're in one sentence. And that's because they are. But sample size is also related to a bunch of other things. So if your sample size goes up, your power goes up. If your sample size goes up, let's go back here to the beginning. If your sample size goes up, here's my sample, then my assumption of normality is met based on the central limit theorem. If my sample size goes up, so see here we had a sample size of 64. If my sample size goes up, the width of my sampling distribution of the sample means gets narrower. If my sample size goes up, then my x-bar gets closer and closer and closer to the mean. If my sample size goes up, then my standard error is smaller, and that's this whole idea of this getting narrower. So there are a whole bunch of things that happen when I have an adequately sized test. So if I get the sample that's large enough from the population, then I will be much less likely to be wrong. When I come up with my conclusion, I get to the end of my test, then I'm going to give the right information to the people who are reading it later. So sample size is a really big deal from just so many different perspectives. I hope these videos have been helpful, and I look forward to seeing you all on Monday.